line integral. Line integral. इस लेक्चर में लाइन इंटीग्रल के बारे में पढ़ेंगे, सरफेस इंटीग्रल एंड वॉल्यूम इंटीग्रल. We are going to cover it in details. First of all, we will see line integral, then we will move to the surface integral, then volume integral will come. It is very compulsory to understand about it. Then we will understand Green's theorem, Gauss's theorem of divergence, Stokes theorem. Yes. So if you don't have understanding about this line integral, surface integral, volume integral, then you will face absolutely you will face challenges while doing studying Stokes theorems. All these three theorems that are important. Remember, line. Whenever we listen this line integral word, just understand one this symbol we will have one symbol. Okay, one symbol. Just one symbol we used for line integral. But when it comes to uh, what a surface integral, then we use double integrals. When it comes to volume integral, then we use three integrals. Why? What is the reason behind it? I will tell you when we will discuss about surface and volume. Right now, our focus is on line integral. I am PPT. As I tell always when I start a lecture, I say that yes, I have PPT. I will read because I will read because I can't write all those contexts that are compulsory. So whatever will be compulsory points, I will emphasize on those words or on those topics. So it is saying let del A, this dl will be our vector. Why this vector symbol is used? That's why. So L means length. Okay, length of the element. Here we are considering L as a length. L as a length. So let's just say we have Z, X, Y. We have a curve A to B. We have a curve A to B. A small length we will take from this curve. A small length. Let's suppose this a dl, this a dl. It is also providing direction because we have this x, y, z coordinates. dl, okay. This is what is a figure of line integral where we have a curve. Where we have a curve. Integral means what? This is line, but what kind of line? Curve line. Integral means what? It says that you are going to add or from initial to final. From initial to final, you will have to add. That is what is the meaning of integration. We do integration so that we can add all those quantities that we need. Okay, that we need if it is possible by the help of an integral. Okay, that's why it is used. So a small dl length we will take from A to B. A small dl. Since it has a what vector? Of course, it is a depend on position vector. It is a depend on position. It will have some x, some y, some z. So of course, it is a depend on position. That's why we need to take a position vector that can be f, that can be A. Right now, just we are considering F as a position factor. F as a position factor. So PPT is saying that DL is the line element of length. This is just line element, a small element of this complete element. Of this complete length, we have this DL, which is a small length element. You can say a small length element of the complete length. Okay. So DL at a point, at this point, at a point on a smooth curve. This is a smooth curve AB from A to B. This is our initial and B is the final. Okay, A is the initial, B and B is the final. Drawn in a vector field. Remember, this is in vector field. Means we have a field which is a vector. So this line, this curve line is present in vector field. Okay, it is present in vector field. So this is not a position vector. It is a vector field. Okay, F means field. Here we are not considering F as a force. We are considering it as a field. Okay, vector field. Since it is a present in vector field. So one point we are taking, one point, or you can say one location, one point function we are taking from the vector field. From the vector field. Okay. From the vector field, which is this point we are taking. Clear? So you saw that F is this F is a vector field. It is a vector quantity because symbol was used. That's why. And DL is a small length element. A small length element. DL is a small length element. Okay. D means a small, L means length, and it is a vector quantity. This is vector quantity. Remember, A is the initial point. A is the initial point. B is a final point. Integral means sum of this small dl according to location, according to point function. We just add, then we get a cap. We get what? This is total length element. Total length element. So if this F vector is a continuous vector point function. Continuous means a small. This is a continuous vector. It is also for continuous means this distance between them is equal. For example, between them is a 2. So over here it should be also 2. Over here it should be also 2. Over here it should be also 2. Okay, length should be 2. This is what is the meaning of a continuous. Okay. When we say body is a continuous, means we are saying distance between 2 points should be same. Okay, should be same. That is what we say by saying continuous. Okay. So line integral of remember, line integral of vector f over AB from A to B. What will happen? This integration we will use symbol from A to B. Limits. This is a limit A to B. From A to B, we are trying to find what is a total element from A to B. Total element. And since we know that all these small elements are present in vector field, so that's why it is a compulsory to take vector field. Otherwise, it will not make sense. So this small f, I think so. Okay, and dl. This is formula. I think it is also formula of vector work done by force. Work done by force. F into ts. Right now, don't focus on work done. Don't focus on work done. So finally, we got this thing, which is integration from A to B, from initial to final, will be vector field dot okay dot vector field dot uh, dl, a small length, a small length. You know we are using dot product, so it can be written as, here angle is, this angle is how much? Angle is 90 degrees, so it can be written as, it can be written as f dl sin theta, not sin theta but cos theta, not sin theta but cos theta, okay? Or you can write it as a mod of f vector dot mod of dl vector cos theta, okay? This theta is the angle between f vector field and length, okay, length, length element. AB, this is a limit. It is a compulsory to apply, so that we can now, yeah, from here to till here we are ending. We are starting from this point and we are ending till this point. Clear? This was very simple form. Now we are in the discussion of vector. This is chapter. Chapter name is vector. So that's why it is also compulsory to see this form into vector form. So how to convert it into vector form? This is very simple. Just write all components of a vector field, all components of a vector field. Then write all components of a small element. Okay, a small element. So this will be our, I think, fx I cap plus fy j cap, that is a, so fx I cap plus fy j cap plus fz k cap. Got it? This is a element, not element. This is a component of a vector field. Clear? Now, what about a dl? dl. This will be our dlx. I think so. Not dlx. Don't take L. So dx I cap plus dy j cap plus dz k cap. This is how we convert a small length element into vector form, which is nothing but dl vector is equal to dx I cap plus dy j cap plus dz k cap. Got it? Whatever we wanted, we got. Whatever we wanted, we got. Now just we will put this in place of f vector f, and this in place of dl, and then use a dot product. Then use dot product. Got it? So our AB will be equal to line integral of AB will be equal to, from A to B, this is how much? fx I cap plus fy j cap plus fz k cap dot dx I cap plus dy j cap plus dz k cap. Now your work is to use or apply dot product. When you will multiple angle between them is how much? 90 degree. Clear? Angle between them is 90 degree. This I cap will become 1. There are two vectors. So cos cos 0. So cos 0 is how much? 1. Cos 0 is how much? Cos 0 degree is how 1. So angle over here in this equation, angle is 0. How did we recognize? Here there are two vectors which are same. So same vectors provides what? Zero angle. So that's why I cap multiple I cap will be 1. The left thing is what? Fx dot dx. Fx dot dx. Limit will be still present. Fx dx plus zz will become what? Fy dy. Got it. Again kk will become 1. Reason is angle is 0. So fz and dz. This is our final equation to apply in numericals when question is asking find line integral and question is providing this vector field, location of a vector field, or you can say location of a vector function, okay, point function of a vector, and it is also providing, if it is also providing or a small length, then we can use this formula. Condition is a question should ask what? Line integral, okay, line integral. Clear? I hope we are clear. Till here this was in simple form, okay, this was in simple form. Just we converted it into vector form, and then we wrote what? Components of a vector field, components of a dl, and then we put this value, or you can say this component over in place of, just we replace this f factor by this component and dl factor by this component. Then we used dot product. After using dot product, we got this thing. Okay, yeah, or you can say it is a derivation. Yeah, this is a derivation. Derivation provides logic. Derivation provides logic. Now we are able to move on the discussion of a surface integral. It is done. About line integral, this is done. Now let's see surface integral. Surface integral. Once you understand line integral, it becomes easy to understand surface integral. Then you understand. Okay, first of all, let us complete what? Surface integral. Surface integral. Yeah, one thing I would like to add for linear integral. Remember, linear integral provides one dimension. Okay, one dimension. That's why we were using single integral. Okay, single integral. But this surface integral provides a double dimension, means a double axis, double dimension, and double integral is used for surface integral, double integral. This is our surface. If you use a single integral, just put this letter s so that anybody can interact with. If you use this double integral and you remove this s, so anybody will say yes, this is a surface integral. How will somebody understand? Anybody will understand that this is a surface integral because there are two integrals. It means two dimensions. That is how anybody will interact. Okay. This is enough. This is enough about the symbol. It's not simple. So PPT is saying area is a vector quantity. Volume is not vector quantity. Remember, area, we are considering area as a vector quantity. But in some area is a scalar quantity. But in some problems, we just consider this area as a vector quantity. In some problem, according to requirement. Okay. Over here, in this context, in this part, we are going to consider the area as a vector quantity, since we know that it is a scalar quantity, but just we will consider that area quantity as a vector quantity. Okay. But in some problem, we take area as a vector, and in this condition, this is known as a area vector. What are we doing? We are considering area quantity as a vector quantity. If we are considering area quantity as a vector quantity, so finally we can say yes, our area is going to be area vector. Okay. So this area vector, this will be our area vector. A means area vector, area of some region, area of some region equal to the area of. So next sentence is the magnitude of area vector, magnitude of area vector. Magnitude of area vector is equal to the area of this surface. Area of this surface. Area of this surface. This will be equal to area of the surface and the direction of the area vector, which will be perpendicular to the plane and radially outwards. Direction will be outward. So you can say this area is a vector. So magnitude of area will be A dot n cap. N cap is a 4 direction. N cap is a 4 direction. Okay. This is what is happening. It is saying that area vector will be equal to magnitude of area vector multiple direction. Okay, direction. Got it? Area figure. Let's draw a figure for a surface center so that we can completely visualize it and get more clarity. If it is possible, yes, it is possible to get more clarity by drawing a figure. Drawing is drawn so that the student can visualize. This is our, let's say, this is our surface. I am talking about this surface, not xy. Xy, we took this as a coordinate so that we can get a location of the vector function point. Clear? Don't think about xy. Don't focus more on xy. Okay. Here your more focus should be on surface. This is surface I am talking about. This is surface. Remember, D is. Keep this in your mind. Here is, I am talking about surface, but D is used, as you know, D is used as for a small. So this will become a small surface, a small surface, okay, a small surface. Here this is also our vector quantity. Whenever I am writing this ds, just you understand, just understand that yes, this is our small surface. Now this a small surface, if we take complete a small surface of this part, what will happen? We will get a total surface. Total surface, to get a total surface, you know, we use integration. We use integration, yeah. Same here, we will use integration because it is a compulsory. What is a compulsory? Again and like, direction will be our outward or inward, okay, outward or inward. We can say this is a vector, so it will be equal to magnitude of a vector and n cap, which is for direction. Work of this vector is to provide the direction, okay. Got it. And here you can see this n cap is perpendicular to plane vertical downward, vertical outward, okay, radically outwards, radically outwards. Outward means this side, got it. So it says imagine a smooth surface. This is a smooth surface. S means a surface drawn in a vector field. Just we took this surface in vector field, and surface is a smooth. Since we are taking this a small surface in vector field, can you use F vector? F is not force over here. In this context, F is not force, F is a vector field. Got it. And a continuously varying vector function F. Vector function F means continuously, if you see for this point, what will be over here? F vector field. This vector field. Continuous means the distance between between 2 points are same. Between 2 points are same. This is what is meaning for continuous. Got it? So this will be our F. It is for vector field, and we are taking this a small ds. This a small ds, a small surface. A small surface is providing vector field, since it is a present in vector field, okay? And it will have a direction which will be outward, radially outward. Simple, you can write this is double integration. This surface integral is equal to double integration your vector field, this vector field dot a small ds. It will give completely entire complete total a small length. This is a small length, okay, a small length. And here F vector is a continuous. continuous varying function. Got it. Got it. Angle between this direction and the vector field is 90 degree. When you will put 90 degree, what will happen? Okay, ignore right now 90 degree. This was a very simple. It is a simple form. Now let's see this into vector form. Into vector form. Let if vector has a fx I cap fy z cap plus fz k cap. These are components of vector field. Okay. Now next vector, which is ds. So dx I cap plus dy z cap plus dz k cap. These were two things that we need. Okay, so let's convert it this equation into in this form. Surface integral of vector f and ds will be equal to double integration s f vector into ds. Just we will put components of this vector, components of a ds vector. First we have fx I cap plus fy z cap plus fz k cap. Okay. Another component dot dx I cap plus dy z cap plus dz k cap. Remember, brother, line integral is a scalar quantity. Surface integral is also a scalar quantity. No. Here we have I, Z, K cap. So of course it is providing. What do you think? Here it is a dot. So don't you think that at the end we will get only magnitude? Don't you think? Think for few seconds. Here we are using dot product, so of course we are going to get the magnitude, not a direction. Okay. What are you understanding from this dot? You are understanding that a scalar integral is a scalar. Surface integral is a scalar quantity, and linear integral was also a scalar quantity. Got it? Simplify it, then see what will come. I into I dot will be 1. So fx dx we have fy dy plus fz dz. This is the last step. Remember, it is a derivation. We will use this last thing in our numericals. Okay, in our numericals. Now let's see volume integral. About the surface integral, it is done. This is enough. It is enough. This is enough. volume integral. Volume integral. Volume has three dimension. Surface had two dimension. So volume has three dimension. Can you use three integral? Yes, you can use. Why you can use? Reason is it has a three dimension. This three integral you can use for volume. For volume. If you remove V later, then still anybody will be able to interact with this three integral. They will say yes, it is volume integral. Volume. Let's explore it in more details. PPT is the same. Let we have a surface enclosing volume. What I understand? Enclosed. Enclosed. If a curve is like this enclosed. This curve which is enclosed. So remember, here our linear integral will be what? Linear integral will be this one integration and this is circle which is telling about closed integral. Okay, closed curve. Got it. Then F vector which is a vector field and a small element length. Okay, this will be equal to 0. Reason is initial and final is at the same point. Initial and final point is at the same location, at same point. That's why integration of vector field dot a small element length will be equal to 0. Final and last endpoints are at the same location. That's why. So I am emphasizing on this symbol and on this 0. Clear? Circle is circle with integration symbol is about closed integral, closed curve. Okay. This was left thing. Now volume integral. Let we have a surface enclosing volume. There is a surface. Surface is enclosed. Okay, surface should be enclosed. All sides where surface are enclosed, what will we get? We will get volume. Of course, one side base, a top side base, let's say base, surface and faces. So all these are closed. So what are we getting? We are getting volume. You can write, if examiner is asking, this question came into your exam, then you can say let we have a surface enclosing volume V and F is a vector function at a point in a small element AB in the region area. I'm talking about area, not region logical. In the region, figure since we are taking volume x, y, z, here we are going to take a small volume of this complete volume, a small volume. Okay, first of all read this statement. Let me have, suppose we have a surface which is enclosed. Okay, enclosing volume V. Here V is a vector quantity. This V is a completely vector quantity. We are not going to consider it as a, hold on. V is a scalar quantity. V is a scalar quantity. We will not consider it as a vector quantity. So V is a scalar quantity. V is a scalar quantity. So don't use this symbol over here. When you are writing dV, it means we have a small volume. We have a small volume. dV means a small volume. Got it? Here, if this F is a vector field. Vector field. This F means field is a vector function at a point. This F is a vector function at a point in a small element dV. Let's say this is a small element dV we are taking, and at the center of this small dV is a what? Vector function point. Vector function point. At the center of this dV, in a small element dV, in this region. So we are talking about this point, which is a vector function point, and we are going to denote it by F vector. Got it? F is not completely vector field. I am just saying that this F vector is present in vector field, and this is a one point which is working as a function. Okay, it is not completely vector field. This F vector is present in vector field, and it is working as a point function. So since it is present in vector field, can you say that this point function is nothing but vector function point? If it is present in a scalar field, then you say yes, this is a scalar point function. Okay, a scalar point function. Got it? So finally, volume integral of this function point over dV over one volume or dV will be equal to volume integral of F vector over one volume which is V equal to triple integration and then point function, vector function point. Okay, now I will call it as a vector function point. So F vector dot dV, don't use a symbol of a vector for dV because it is a scalar quantity. Got it. Now this is a simple form. Let's convert this simple form into vector components. If it can be written as fx I cap plus fy j cap plus fz k cap. But don't write dv as a dx I cap plus dy z cap. No, this is wrong. Okay, so dv which has three dimension. So you can write dx, dv, no, dx, dy, dz. This a small dx, a small dy, and a small dz. Okay. This volume we are taking a small volume. Length of this a small volume. Dot with a vector point function, vector function point. Now just substitute value of this and value of this dv in this equation. This will become fx I cap plus fy z cap plus fz k cap dot with the dx dy dz. How did it come? It came for a small length, height, width for a small volume, and this is a location of a vector function point. Clear? Clear? That's it. Then you can simplify it one more step. Till here this is enough. This is enough. Volume integral of vector function point over dv, or you can say dv. That's it. This was about line integral, surface integral, and volume integral. Now next, divergence of a vector field. Next topic is divergence of a vector field. Divergence of a vector field. Divergence of a vector field means a vector in a vector field. In a vector field, there would be vector which is a diverging. What do you think about divergence and curl? Divergence and curl. Curl and this phi. Phi means a scalar field. Okay. You know this phi. This divergence means it means something is diverging, or you can say liquid is diverging. Liquid is diverging means liquid is spreading out, So divergence means something is spreading out, and curl means something is rotating. Now here something is nothing but vector. If a vector is rotating, we will say a curl of vector is not equal to 0. Reason is vector is rotating. Divergence means divergence of any vector means that vector in the vector field is diverging. Okay, diverging. This is what is the meaning of a divergence. Okay. This was a little about divergence vector. I explained it over here so that you don't get confused when I am talking about the divergence of a vector field. What is vector field? Vector field is a field where there are a lot of vectors which are present in a vector field. It would be diverging or it would be converging. It would be diverging, it would be converging, or it may be rotating. Some such conditions you will observe when questions will come related to curl. So in vector field, what can happen? In vector field, a vector will be diverging, what vector will be converging, vector will be rotating, vector will not be rotating. All these things will be happening. Okay. So statement for this divergence of a vector field is the divergence of a vector field. The divergence of a vector field at any point is defined as the amount of magnetic flux. Flux means how much lines are entering and how much lines are leaving from something. This is what is the meaning of a flux. So we have a magnetic flux lines is the amount of magnetic flux per unit volume diverging from that point. The divergence of a vector field at any point is defined as the amount of magnetic flux per unit volume means 1 by V diverging from that point means per volume how much amount of magnetic flux is diverging from that point. We will take one point and at that point in a vector field how much amount of magnetic flux is diverging. That is what we get from divergence of a vector field. Got it? So this was some sentences that we need to write when we are writing about divergence of a vector field. Okay. So in short, you can say rate of flow. In short, rate of flow of flux means lines or a fluid means how much fluid per unit volume diverged, or you can say left or entered. Okay, how much fluid or how much flow of flux went from per unit volume. Got it? So in short, you can say rate of a flow of a flux or liquid fluid. Now let's see derivation of expression. Derivation of expression. From here we start. So let me draw a figure so that we can get more clarity. So that we can get more clarity. This is our figure. Why did we take a volume, this shape? Because we are talking about volume, per unit volume, per unit. Anything can diverge from surface as well. So here we took a volume, okay, volume. Remember, this is a very small volume. So this will be how much? Del z. This will be del z, or you can say, a small height. Since it is a small volume type, for a small height, dz is used, and this will be our dy, and this length will be dx. Got it? What are you understanding by dx or dy? Dz means these are dimensions. Dx, dy, dz, all these are a small. Okay, a small. Got it? Take one point which is a center, of this volume. So center will be, this will be center. This point you have to take, and coordinates of this point will be what? Nothing but x, y, z. X, y, z. This is a C. X, y, z. Remember, it is a coordinate of the center, Clear? Clear. AD is equal to dz, and dp is equal to dx, dc is equal to dy. Got it? Let us consider a small parallelepiped. This is nothing but parallelepiped. It is not completely circular. This is not completely circle pipe. It is a parallelepiped. Okay. Parallelepiped. Was the center C, this at a point x, y, z, and whose sides are this dx, dy, dz of a volume. Okay. Velocity of the fluid. Velocity is coming from this surface A, B, C, D. From this surface, velocity is entering. With how much velocity? Question is with how much velocity? And with how much velocity the same fluid will leave from this side, from this surface, which is a PQRS. Okay. We are taking two surfaces, this ABCD and PQRS. From this surface, fluid will enter, and from PQRS, this surface, liquid will leave. But main point is with how much velocity? So tell here, these are what? Let us consider a small parallelopiped whose center C at point x comma y comma z and whose sides are dx dy dz. Velocity of the fluid at point C is given by whatever we saw in this diagram. Just we wrote in statement in the form of a statement. Let us consider a small paralleloparallel. This is a small paralleloparallel and whose center is C, whose coordinates are x, y, z, and whose sides are dx, dy, dz. These are small sides of this small volume. Velocity of the fluid. Velocity is the entry with velocity. So at point C, from this point C is given by So first equation will be for velocity Vx I cap plus Vy z cap plus Vz k cap. Just we broke this velocity vector into components. Okay, just we brought this velocity vector into components. So velocity of fluid will be this much. Okay, for x component, remember, for x component of velocity at ABCD. Look at over here. You will have to analyze over this part. What is it saying? This is statement for x component. For this x component, velocity of a fluid from this surface will be how much? That is what it is saying. This is explain for x component. Okay. You are understanding that from ABCD surface, fluid is entering, fluid is coming with some velocity which is with respect to dx. So you can write this as a Vx minus dvx upon dx by 2 into dy dz Try to understand. This is velocity. But along x component, velocity of a fluid along x component minus a small dvx upon dx means what is the changes of this vx with respect to dx. What is the changes? dv here vx, this is nothing but velocity of a fluid, but along x we are not taking along y, along z, only we are taking along x. What is the velocity of a fluid? That is what we are understanding by this vx. Okay, now dvx dvx upon dx. What is the meaning of it? It is explaining that what is the changes of dvx, or you can say velocity of a fluid along x with respect to dx. What is changes? What is changes of a velocity of a fluid which is along x with respect to dx. So with respect to this dx, what is changes in velocity of a fluid? This is what we are understanding by this thing. Got it. What about dx upon 2? dx upon 2. dx upon 2 means this half we are taking. This half. dx by 2 plus dx by 2 will be complete. So just this full dx, this dx is full. Just half of this dx will be 2 dx upon 2. So one thing we are taking dx upon 2. One this part. So what will happen? This fluid when it will enter from this surface, when fluid will enter from this surface, so a small this dx by 2 will go forward, a small dx by 2, this much will be covered by fluid dx upon 2. So dx upon 2 is nothing but length, half length of the dx, okay, of the dx. Got it. And dy into dz, this is what dy, whatever left things are dy dz, just write over it. We will take a complete dy and dz, but don't take a complete dx. Here we will have to take dx by 2. Okay. So subtract this thing from complete vx. Subtract this thing from this. So this is changes. This is changes from here. Velocity was complete dx, and just this changes we are taking with respect to dx, and length is this much dx upon 2. This is what is a length. Okay. dy into dz. We will take this completely dy dz. Don't take dy as a dy upon 2, dz upon 2. No. Reason is we are taking velocity along x component. Okay, that's why. That's why. So what is happening over here? Minus. Minus is about changes. Minus is about changes. Now next. X component of velocity at next surface. Next surface is what? PQRS. PQRS. Try to understand. This liquid fluid which came from this surface, this much it went up from here to till here. So this and now we are taking same component but at PQRS. Okay, from surface of PQRS, same component but surface is different. Initially surface was ABCD and final surface is a PQRS. Okay, so for next word you can take positive sign, from backward you can take negative sign. Everything will be same. Vx plus dvx upon dx dx upon 2 into dy dz. Try to understand what is negative working over here and what is positive working over here. Negative is about it went from here to till here, from here to till here it went, and positive is about this much went from here, from this surface outward. This is what is about positive. So this negative positive will give us what? Sum of positive negative will give us net flux. Net flux, okay. Net flux means percent of liquid in volume was how much when velocity was entering with this much velocity, when velocity fluid was living from this surface with this much velocity. So at that point, how much fluid was present in the volume? How much volume? So net flux inside the net flux inside the parallel part due to phase ABCD and PQRS. Just you will have to take this velocity and this velocity. Vx plus dvx dx into dx upon to dy dz. Then negative final minus initial will give us a net flux. Okay, so this final minus initial, this Vx minus dvx upon dx upon 2. Everything will be same except a negative sign. dy dz. dy dz. dy dz. Look at over. Till here we are crystal clear about it. Okay. Now we can simplify it further. This negative will become positive, you know. Next it is a calculation, or you can say our duty is to simplify it. Let's see. Let's see. So after simplifying, we will get dvx upon dx upon 2 dy dz plus dvx upon dx upon 2 dy dz. Try to understand how did it come. How did? Look at over here. just negative became positive. Nothing else. Negative became positive. Look at over here. Vx plus dvx upon dx dx upon 2 dy dz minus vx minus ddx upon dx dx upon 2 dy dz. What is happening over here? This minus positive, this minus positive. But this Vx will become negative and this minus dvx upon dx will become positive. So this Vx will cut to each other. Okay. So finally we have dvx upon dx upon 2 dx upon 2 into dv dz positive. This minus positive. So dvx upon dx upon 2 and dy dz. Try to understand. Here you can see this is velocity of fluid along x with respect to dx, and dx upon 2 is nothing but half length of dx. Okay, dy is the next length and dz is also next length. That is how this came from this equation. Got it? From this equation. Now next. Try to understand. This is becoming dvx. You replace this d by curly d. Okay, curly d. So dvx upon dv dx dy dz. How did it come? Curly d. Here this is what? It is common. This is common. This is common. This common we wrote over here. Dx dy dz. This is also common. So finally you will get this final thing, which is a dvx upon dx and all three dimension dx dy dz dz. Now this was about net flux which was present, which liquid or fluid was present in the volume. This is our net flux. So you can write net flux inside the parallel part due to other four faces are curly dy velocity of fluid along y upon dy with respect to dy, and dx dy dz. Okay, for four faces, and along z this will become dvz dz dx dy dz. This is along z and it is along y. This was along x. Okay. Okay. Now let's find the total flux inside the parallelepiped for all faces, not only ABCD or PQRS, for all faces. In that case, we need to do sum up. We need to do sum up. Take this, and this, add all these three, then you will get a total flux. Which are present. What are present? Fluid is present inside the parallelepiped. That amount of fluid we will get. Okay, amount of fluid. Flux means amount of fluid in this context. So total, finally you can write total flux inside the parallelepiped is equal to, take part this dvx dx dy dz. This is a value of a volume, dv. Okay, dv. You can write dv is equal to dx dy dz. Clear? And this is nothing but change in velocity of this dbx upon dx is what? Change in velocity of fluid along x with respect to dx. This is what is meaning of this thing. Okay, plus curly dy upon dy with respect to dy, then dx dy dz. Here we can get confused, but try to focus completely on your discussion so that you cannot distract. Okay, you can't distract. Last we have z component, dvz upon curly vz upon curly z, dx dy dz. Okay, here you can see what is common thing in this. Common thing, this is not common. Here you can say this is vx, vy, vz. It's not common. Dx, dy, dz. This is common for each term. Yeah, for each term. So that's why we can write dx, dy, dz outside. We can represent this outside from curly dvx upon x plus dv vy upon dy plus curly vz upon curly z. This is the last thing. Okay, last thing. Since you know that per unit volume is nothing but 1 upon v, and v is nothing but dx dv dz, so per volume of the parallelepiped per unit will be our 1 upon dx dv dy dz. So you can write flux per unit means per unit volume, how much flux amount of fluid we are getting per unit volume. Okay, for per unit volume flux per unit volume of the parallelepiped which is equal to look at only dx dy dz and upon dx dy dz, both will cut to each other and we will get only this thing. So dvx upon dx plus dv upon dy plus dvz upon dz. This is a final equation that we need to apply in our upcoming question. So flux per unit volume. Remember, this is a per unit volume. Okay. Change in velocity of a fluid along x component with respect to dx plus change in velocity of a fluid along y component with respect to dy plus change in velocity of fluid along z component with respect to dz. This will give us flux means amount of fluid per unit volume of the parallelepiped. From the parallelepiped we will get amount of fluid per unit volume. Okay, per unit volume. And now you can see, brother, what is happening over here. You can simplify it furthermore. This of d upon dx plus d upon dy plus d upon dz is nothing but this is a del operator. Yeah. And we will get vx, vy, vz. It is a vector of velocity. So can you write this like this over here? Or you can write over here dx plus, or you can say I cap I cap okay. Then we have d upon dy z cap plus d upon dz k cap dot since it is also in vector form and d upon dx is also in vector form, so this will become vx I cap plus vy j cap plus vz k cap. Okay, now this is our del operator. Dot will be same, means a scalar product, and this is our vector of velocity, and you can write this as a divergence of a velocity vector. Yes, del operator can be called as a divergence or it can be called as a curl. Okay, curl. This is our final. You can see how did it come. Flux per unit volume. Here just we used 1 upon dx d upon dz, and then we saw that this is nothing but a del operator, and then dot vx I cap plus vy j cap plus vz. That thing we observed. Then we just wrote this separately. Then this is nothing but del operator and it is nothing but velocity vector. So divergence of a velocity. Velocity is diverging. Velocity of a fluid is a diverging. Clear? That is how you will write the divergence of a vector field.